Welcome to the Deep Dive. We're really glad you could join us for this session of For the Love of Physics.
Mhm.
And hey, a huge shout out to everyone at Ishik Boys High School listening in, especially if you're in Mr. Jager's physics class. We know you're working hard, getting curious about how the world works, and today we're diving into something that's happening all around you, all the time. Relative motion. Ever, sat on a bus, completely still, and the bus next to you starts moving. And for just a second, it feels like you're the one rolling backward.
Oh, yeah. That weird feeling. Happens all the time.
Exactly. That little bit of confusion. That's relative motion. It's basically the idea that how you see movement, well, it really depends on your viewpoint, where you are if you're moving.
It's not fixed.
Right. So today, we're going to break that down, make it make sense. So the first big idea we need is something physicists call a frame of reference. What is that exactly? Why is it so important?
Well, think of it like this. A frame of reference is just your perspective. The viewpoint you choose to observe something from. It could be you standing still on the ground, or sitting in a moving car, or even on a spinning merry-go-round. It's your personal observation post.
Okay, like my own little bubble I see the world from.
Pretty much. And what's really interesting is how much that chosen frame changes what you actually measure. Let's grab that car example. Imagine you're driving, say, 80 kilometers per hour, heading north.
Got it. Cruising along.
Then another car, going faster, passes you, also north, but at 90 kilometers per hour. Now, from inside your car, what does that look like? How fast does that other car seem to be moving relative to you?
Well, they're only going 10 kilometers faster than me, so it'd feel like they're just slowly pulling away, right? Like 10 kilometers.
Exactly. It feels slow from your frame of reference.
Okay. If I wasn't in the car, if I was standing on the sidewalk watching both cars go by.
Completely different picture from the ground frame of reference. You'd see that faster car zooming past at its full speed, 90 kilometers per hour.
Whoa. So same car, same moment, but 10 kilometers from my car's perspective, 90 kilometers from the ground's perspective. How can the same motion look so different?
Because velocity, displacement, acceleration, all these things we measure, they aren't absolute. They depend entirely on the observer's frame of reference. If observers are moving relative to each other, they just won't agree on those measurements. Your car becomes your reference point, and you only perceive the difference in speed.
So my own motion actually changes my perception of other motions.
That's
a bit of a mind bender.
It really is. It tells us there's no single true speed. It's all relative.
Okay. Does this apply to, like, more extreme stuff? You mentioned an airplane example, dropping something.
Oh, absolutely. The stunt dummy example is perfect. Picture this.
Yeah.
An airplane flying nice and level, constant speed, constant altitude.
Steady flight.
Right. And then they release a stunt dummy from the plane. Now, if you're a passenger looking out the window, what do you see the dummy do?
Well, the plane's moving forward, but relative to the plane, I guess I just see it fall straight down, like right underneath me.
Exactly. From the frame of reference of the plane, the dummy appears to fall vertically, straight down.
Okay.
But now, switch perspective. Imagine someone standing on the ground watching this whole thing. What do they see?
Okay. The dummy was in the plane, so it had the plane's forward speed rate.
Precisely.
So from the ground, it wouldn't just drop straight down. It would be moving forward and falling. It'd follow a curve, like a projectile.
You got it. For the ground observer, the dummy follows a parabolic path. It has its initial horizontal velocity from the plane, plus the vertical acceleration due to gravity. And here's the really neat part. If we ignore air resistance for a moment.
Which physics loves to do.
Yeah, makes things simpler to start. That dummy, even though it's falling in a curve relative to the ground, it actually lands directly beneath the airplane, assuming the plane keeps flying straight and level.
No way. Really?
Yes, because it keeps that same horizontal velocity as the plane. So relative to the plane, it just goes straight down. Relative to the ground, it follows the curve, but stays aligned horizontally.
That's incredible. Same event, two totally different observed paths. Frame of reference is everything. Okay, so let's try a quick brain teaser for everyone listening. Imagine you're in an elevator going down.
Okay.
And you're bouncing a little rubber ball. Now, the elevator starts to slow down as it approaches a floor. Right at that moment, you just drop the ball. The question is, relative to the elevator, is the ball's acceleration less than, equal to, or greater than its acceleration relative to the ground, which is just g, right?
Ooh, tricky one. Think about the forces and the change in the elevator's motion.
Yeah, no need to shout out the answer. Just chew on that one for a bit. Think about those reference frames. All right, so we've kind of grasped the what of relative motion, but how do physicists actually, calculate things, put numbers on it, especially when things get more complicated than cars on a straight road?
Right, intuition is great, but sometimes you need a solid method. And this is where we get into solving relative velocity problems systematically. It's less about one single formula and more about a technique, a way of thinking using subscripts. Let's go back to those cars.
Okay, the 80-kilometer one and the 90-kilometer one, both going north.
Yep, let's label things. S for the slower car, F for the faster car, and E for the Earth, our ground observer. So the velocity of the slow car with respect to the Earth is written VSE. That's plus 80 kilometers if we say north is positive.
Makes sense. VSE was plus 80.
And the velocity of the fast car with respect to the Earth is VFE. That's plus 90 kilometer. Got it.
VFE equals plus 90.
Now what we wanted to find was the velocity of the fast car with respect to the slower car. That's VFS.
Right. How fast the fast car seems to be moving from the slow car's perspective. How do the subscripts help us build the equation?
Think of it like connecting dots. You want to relate F to S, VSS. You know F relative to E, VFE, and you know something about S relative to E, VSE. The trick is to link them through the common frame Earth, E. So you write VFS equals VFE plus VS.
Ah, I see. The E's are like the interconnection. The last letter of the first term, VFE, matches the first letter of the second term, VE. F to E, then E to S gives you F to S.
Exactly. It's like planning a trip. Go from F to E, then from E to S.
Yeah.
The overall journey is F to S. And remember, these are vectors, so direction matters.
Okay, that structure makes sense. But wait, we have VSE, slow car, relative to Earth. What's VES, Earth, relative to slow car?
Good question. It's just the opposite. If the slow car S moves at plus 80 kilometer relative to Earth, E, then from the car's perspective, the Earth E seems to be moving backward or south at 80 kilometers. So VES is the negative of VSE, VES, and that's VSE.
Perfect. So
Yeah.
putting it all together for the cars, VFS equals VFE plus VES. That becomes VFS plus 90 kilometers, which equals VFS is plus 10 kilometers. And the plus car tells us it's north.
Which is exactly what your intuition told you at the start. The fast car seems to pull away northward at 10 kilometers relative to the slow car.
That is so cool when the math lines up with what feels right.
It is. And this subscript technique works for any relative velocity problem. It's not just one equation. It's a way to build the right equation every time.
So it's super flexible.
Exactly. Which, raises the question, where else does this pop up? Especially when things aren't just moving in a straight line.
Well, here's one for you to think about, maybe something you've seen in movies. Aircraft carriers. Why does a plane trying to land on one always approach from the rear of the carrier? Why not try to land coming towards it, head on? Think about relative velocity. How fast would the plane be moving relative to the deck in each case? Something to ponder. Now, let's tackle another class example, one you definitely might see in class. The boat on a river.
Ah, yes, a good one.
Okay, imagine a boat. Its engine can push it at, say, 10 kilometers per hour relative to the water. And the boater wants to go straight north, directly across the river.
Okay, aiming north.
But the river isn't still. It's flowing steadily eastward at 5 kilometers per hour.
So the water itself is moving sideways.
Right, so the question is, what's the boat's actual velocity, its speed and direction, relative to someone standing still on the riverbank on the Earth?
This is where drawing a picture, a vector diagram, really helps. You've got two velocities acting on the boat relative to the Earth. You have the boat's velocity relative to the river, VBR, which is that 10-kilometer arc pointing north.
Okay.
Let's draw that as an arrow pointing up.
Okay, arrow up.
Then you have the river's velocity relative to the Earth, VRE, which is 5-kilometer arc pointing east. Draw that as an arrow pointing starting from the tip of the first arrow.
Like adding arrows head to tail.
Exactly. Vector addition. The boat is trying to go north through the water, but the water itself is carrying it east relative to the ground. So the boat's actual velocity relative to the Earth, VBE, is the result, the arrow that goes from the start of the first vector to the end of the second vector. It's the diagonal.
And hey, because north and east are perpendicular, those two arrows form the sides of a right-angled triangle.
Precisely. And that's key.
Which means we can use math we already know. To find the magnitude of that diagonal velocity, the boat's actual speed relative to the ground, VBE, we just use.
The Pythagorean theorem?
Yeah. A2 plus B2 equals C2. So VBE2 equals VBR2 plus VRE2. You square the north speed, square the east speed, add them, and take the square root.
That gives you the boat's actual speed over the ground.
And what about the direction? It's not going straight north anymore, it's going diagonally. How do we find that angle?
Trigonometry. Since we have a right triangle, we can use sine, cosine, or tangent. Tangent is often useful here. The tangent of the angle, let's call it theta, east of north, would be the opposite side, the river speed, VRE, divided by the adjacent side, the boat speed relative to water, VBR.
So tan theta VRE VBR. Then you use the inverse tangent function on your calculator to find the actual angle.
Yep, and this isn't just, a made-up physics problem. This is real life for pilots dealing with crosswinds or sailors navigating ocean currents.
Right. They have to account for the movement of the air or water itself to figure out their true path over the ground.
Exactly.
Yeah.
They need to calculate their velocity relative to the Earth to actually get where they want to go. It's practical physics.
Wow, okay. So let's quickly recap what we've unpacked in this deep dive. First, the big idea. Motion is relative. What you measure depends completely on your frame of reference.
No single true velocity. It depends on who's looking.
And that means velocity, displacement, even acceleration measurements can differ between observers moving relative to each other.
You saw that with the cars in the stunt dummy.
Then we found a systematic way to solve these problems using relative velocity and that handy subscript notation. VAB, fiery VAE plus VEB.
Remembering that VEB is dash in VBE, the notation keeps track of everything.
And finally, when motions aren't in a line, like the boat on the river, we use vector addition, drawing diagrams, and using tools like Pythagoras and trig to find the resultant velocity.
Tools you're already learning in math apply to understand motion.
So let's leave you with that aircraft carrier question again. Think about it. Why approach from the rear?
How does relative velocity make that landing safer and more manageable for the pilot compared to, say, a head-on approach? What's the key difference in relative speed to the deck?
Definitely something to discuss with your friends, or maybe ask Mr. Jaeger about his thoughts. Stay in contact with your physics teacher, stay creative,